Hello everybody, my name is Wolfgang Maß. I'm at the German Research Center for Artificial Intelligence and I'm working on smart service engineering in industrial settings, healthcare settings and other domains. I want to show what we are doing with respect to what we call collaborative learning in the next couple of slides. So our background motivation for our work is that we are investigating smart services, which can be considered as software systems that adapt to user needs and are adaptive to various kinds of contexts in the real world. And smart services apply AI technologies, processing box data, but also streaming data. And smart services shall be interoperable and shall collaborate over the network, in particular the World Wide Web. There are some goals that we investigate. On one hand side, we want to investigate smart services that only live in a browser and not so much in data centers. Smart services shall be quickly built and shall be based on reusable software modules. We do not want to exclude cloud-based AI services, but want to merge locally executed AI services and cloud-based AI services. Another goal is that smart services are self-descriptive and in this sense self-containing. And they shall be self-maintaining to a certain extent, while this at the moment is rather a goal than that we actually have implementations on that. Furthermore, we do not want to confine ourselves to a very specific architecture, but by adopting an agent-based approach, agents shall communicate with each other. They should also dedicate roles to agents, such becoming a server role or a communication partner role, and that should be done dynamically in negotiation between agents. We have built a platform called TUCANA, whose architecture you see on the right-hand side of the slide. And TUCANA is a peer-to-peer architecture where different kind of environments, what we call TUCANA environments, TNs, can communicate with one another. In each TUCANA environment, several smart services can be executed. They can communicate locally, but they can also communicate via peer-to-peer networks based on WebRTC. Each smart service, as you can see on the second image on this slide, consists of different kind of minions, and these minions are software modules with dedicated tasks. We distinguish between perceiver minions, thinker minions, communicator minions, but also actuator minions. The basic minions, according to a three-layer architecture, are perceiver minions, P-mins, and thinker minions, and communicator minions. Perceiver minion collects data and stores the data in the local database of the browser. The thinker minion accesses the data and processes by leveraging data analytical software, in particular TensorFlow-based kind of analytics, but it could be any kind of JavaScript, machine learning software or customized software, while the communicator minion either communicates with other smart services locally via peer-to-peer network globally, or with the end user via the browser interface. We are using JavaScript for all our implementation, WebRTC. For access control, we use Open Authentication 2.0. We are able to export the data that we collect into JSON LD. One implementation is using BabelNet as the transformer basis. We also leverage TensorFlow, and we are compliant with the specification of Gaia X and the International Data Space, which is a widely used kind of specification for Industry 4.0 applications. So we specify the smart services in JSON format, and we use these JSON formats in order to bind the software configuration, the smart service configuration, to pre-installed minions. Probably more interesting for this workshop is the Thinker minion. I have here an example that we use for activity recognition in a shopping context. You also see here that the minions again have an activate method, a notified method, and a terminate method. But in between we also have a method for predict partially. The data that is coming in streams for the acceleration and the geolocation is used to make predictions, and we are using a model that was pre-trained in a sample side, and during the activate method we load that model and we use it to make predictions. In this case it is a very straightforward and simple prediction, simply to say that a person is tired or it's not tired, and the integration of tensorflow.js works quite nicely. On the right hand side you see the model topology that we use here. It is based on LSTM layers and a fully connected layer, and we integrate that all together and push that into our T-minion. Here is the example for the whole smart service for shopping, and as you can see on the left hand side we have a configuration file for our smart service that says that we have two perceiver minions, one for geolocation and the other for linear acceleration. We have one T-min for activity prediction and three C-mins. The one for communicating with the user for a shopping deal that might be appropriate in that situation. We have a peer communicator that can pass information to internal, locally defined, or via a peer-to-peer connection also to external smart services. And we have another communication minion that shows the acceleration also to the user. And this configuration in JSON is very handy and allows us very similar to the architectural and topology of a machine learning model to define smart service designs. Okay, so let's wrap it up. What are our lessons learned, and where do we see potential for further development and specifications? First, it would be interesting to have agent-oriented architecture better being supported by current systems in JavaScript, by WebRTC, and by other technologies. That's one element. Then on the machine learning side, it would be really great if also on the JavaScript side we would have some support for federated learning, distributed learning, and reinforcement learning. This is currently missing. In WebRTC, I know that the signaling service and the protocol is outside of WebRTC. However, I would appreciate, and I think the community would also appreciate in general, an optimized signaling protocol, maybe also an environment for testing for signaling services. And last but not least, Open Authentication 2.0. It requires always on at the moment. If you are offline, Open Authentication is a pain, so you have to switch it on and off. A buffering service for Open Authentication that supports offline services would be really appreciated.